Hey guys, welcome back to another session. Today we're going to look at branching using Python in Grasshopper. And for this exercise, I prepared a two-part script, which will first develop kind of the branching algorithm using the Python plugin in Grasshopper. Then we're going to extract the curves that are output from the plugin and do some topological modeling with it. So this is the final result, and I was able to put a lot of variation with it. Basically, it's a simple L system. L system is there's a recursive rule that basically propagates throughout the system, right? So in this case, we have a linear branching mechanism. We're going to first investigate how the branching works in 2D. Then we're going to look at developing it in 3D. And then output curves that we can turn to surfaces using piping functions. So I'm going to start this exercise in 2D. So first thing we're going to do is you go to the mathematics tab, and under that we're going to work with Python. So you just double click, and we have the built-in functions here, and we incorporate import Rhino script syntax as RS. So first thing we're going to do is look into recursion in 2D. So you know that we can create 2 points. I'm actually going to zoom into this screen a bit. So we can create 2 points. Let's say our points are A and B, and I'm going to move my point towards the X direction. And then I can do L equals rs.addLine, and I can just simply pass in A and B. And this L could be the output, right? So if I rename this guy as capital L, and I double click and do a test, let's see, test, okay, and there is my line. So that's the output. I'm going to disable the grid so that we can see it a bit better. There it is. So actually, let's put the maybe the axes. Let's show the grid so that we can see it. Perfect. So what we want is we want this to bifurcate. We can also do a simple recursion where this keeps going in a linear fashion. Actually, maybe we do that first. So let's create a variable and call it generation, or gen for short, and then I'm going to pass in a variable like 5. Then inside Python, what we can do is we can actually advance this line or this point 5 times using recursion. So we can do it simply like this. So while, or we can do while, let's say we create a variable here, count equals 0, while count is less than gen. We're going to do something, and then inside of it we're going to increment count by 1. Right, so here what I want to do is basically draw a line, so something like that. So we can actually define it as a function, call it define grow, and for this one we can pass in a point, a vector, and that's pretty much it. And this can return a new point. So there it is. That's the output, right? So inside of the while loop, what I want to do is initially start calling this function, and then use the output of that function to call itself again, right? So what we can do is, let's say B is not a point anymore. I'm going to delete this L. B is actually, let's say, a vector, and that vector is pointing in the X direction. So what I want to do is here call grow and call A and V, right? So I'm going to pass in the point and the vector to this function, and inside this function, what I want it to do is find a new point. So that new point would be rs.pointAdd, which we could add a point to a vector, and that will give me a new point. And then I can define a new line, right? So I can do L equals rs.addLine, and we can draw a line from point to new point. And then these lines, we don't have to return them, but necessarily we can actually keep adding them to a list. So we can call them as lines, and then I can do lines that append L. And inside of here, inside the while loop, so what's going to happen is we created the point, we created a vector, and while this condition is true, we're going to grow this point towards the vector direction, right? So I'm calling this function, and that function takes in a point and a vector, defines a new point, draws a line to that new point, adds that line to the list, and then returns the new point. So this grow returns a point where we could store it as a variable. And that could be simply a, because we can actually override a. So a would be advancing as the algorithm is recursively moving in the direction of the x-axis. And I think this should work. But we can also do, now that we have a lines list, we can actually rename this as lines and test it again, and there it is. So this is our straight line. So if I bake these, you can see that they're made out of these individual steps where the geometry, the point, is advancing in the x direction. So I'm going to delete this for now. What we want to do is a bit different than this. So what we want to do is we want this line to bifurcate. So we want it to do something like this, right? So I'm going to, let's do scale. So I want it to bifurcate. Basically that will require the vector to turn to left and right. So if I have a vector, I need to define two new vectors along this axis that is in the middle. So I need to rotate it left and right, and that will create this bifurcating function, and we can keep doing it recursively. So all I have to do is actually adjust my growth function. Because we are calling it here, I'm actually going to do this a bit different now. So rather than having a while loop here, we can actually do it like this. We actually can just start with the point and a vector, or we can actually, yeah, let's start with the point and a vector, and I can delete these, and I can also pass in a variable that is 0, and that could be let's call it g, the current generation. And inside growth, if current generation is less than gen, which is a parameter, then we can do something here. Then we can do the growth, right? So I'm going to first restructure this, and this actually doesn't have to return anything anymore. It can simply call itself. So that's the idea of recursion. So it can call itself with new point v, and we can do g plus 1, right? So that's essentially what it is. So when I call grow, this function, inside this function, we have a mechanism that checks if the generation is less than 5, because we want to do this operation 5 times. So eventually, because we are calling itself, we are also incrementing this variable called g. It will essentially be 5. So this won't execute anymore. If we don't do that, it's a function that calls itself. It is essentially what recursion is, but it will do it infinitesimally. So it won't stop until there's a terminating condition. So I'm going to do test, and it actually outputs the same thing. Now, because we built it like this, we can actually do something a bit different inside this function. So rather than doing, let's say, growing one in the straight direction, we can actually do two directions, right? So we can actually do, I can define a v1, which is rs.vector rotate. So I want to rotate, let's say, this vector minus 15 and use the z-axis for rotation. And then I can do pt1 equals rs.point_add. So I want to add point and v1, right? So that will be point 1. And I can simply copy this and change this to be positive and redefine this to be v2. And then I can do L1 would be from point 1 to new, so L1 would be from point to point 1, right? So this would be point to point 1. There's no new point anymore. And L2 would be actually point to point 2. And we can simply add these to the list, right? And then what I can do, L2 here, and then I can call the grow function twice. So I can call it with point 1 using v1, and I can call point 2 using v2. So that will create that bifurcating effect, right? Because here I'm checking my code, it should work. So let's see, let's test it. It says point 2 is not defined. Line 16, where it is point 2 here. So I'm overriding point 1, so I'll do just point 2, test. v1 is not defined. Where's v1? v1 is here, v2 is here. Now these have to be capitalized. So v1, v2, test again, and there it is. So we don't have the initial branch, which could be simply added here. So if you do, for instance, rs dot, so we can do another L here before we call the grow. L equals, actually, let's go up. So here we have A and V. So we can do L equals rs dot add line, rs dot point add. We want to add A to V, and we want to draw a line from A to AL, and we want to append this to lines that append. But actually we want to pass this new point, so we can actually define it as B, right? So B equals rs dot point add A to B, A to V, and then we can just draw a simple line from A to B. And here, instead of A, we can use B, so that this would be displaced a bit more. So there it is. So we draw a line first and then start bifurcating. So essentially, this is what recursion is. So this is the 2D version. What we want to do, though, is a bit more complex. We want to do this in 3D. So we want to first move this in the vertical direction, and then we want to rotate it in random angles. So that's actually what we're going to work on now. So I'm going to start with, let's see, looking also at my notes. So we actually have to start moving the first line in the vertical direction. So rather than using in the X direction, we can actually use it in the Z direction. And because I'm doing a vector rotate here, that's actually not going to work. So we cannot rotate a Z vector in the Z direction, right? So that will rotate along itself. So instead of that, what we want to do is define a plane here that is at the end of the first curve. So I'm going to just disable this line first so that the recursion doesn't run. So here you can see we are now shooting upwards, and I'm going to just do a plane. Plane equals rs dot add plane from normal. Plane from normal. Let's see. Actually, rs dot plane from normal. Plane from normal. And that is actually what it needs. Is if you look at the specifications below, it needs an origin and a normal. Origin is point and normal is v. So we get a plane oriented to the end of the end of this line, and then we can do we can basically evaluate a random point. So imagine we want to rotate this line. So if I have a plane at the end of this line, right? So there's a plane there. So what I want to do is evaluate a random point. Let's say that random point is here. It could be anywhere we want actually. But let's say that random point is here. And I'm also going to bake this output so that we can use that. So I want to first evaluate a point, then I want to draw a new vector into that direction, and I want to use this to rotate the vertical vector, because for the next generation to grow, we need another vector in this direction, right? So what I want to do is rotate this guy along this vector, so it could rotate. So grabbing a random point on this plane is important because it can we can basically start rotating the vector in different directions using that random point. So I'm going to do basically we got the plane, then I want to get a random point, and random point is just going to be rs.evaluate plane, and I want to evaluate that plane at a random interval. So we want to evaluate the plane, and I can simply do random. We haven't imported random, so let's import random dot uniform, and we can pass in -1 to 1, and I can do this twice because evaluation requires an UNV output. So this is basically -1 to 1 means we want to move, if we normalize the plane, we can move in the minus direction or in the positive direction, and we can get any type of evaluation. And this will give me basically a square. That is, the square center will be located at point, and whatever point I evaluate on that square, it will define a random rotation direction. So we can define a new rotation axis. So we can do it rotation axis equals rs.vector create, and that will be random point to point. So that's actually this vector now. So this vector will be my rotation axis. And then we can actually do our vector rotations using this axis now. So rather than using z, I can do rotation axis. And that's pretty much it. And we can, I can also do the same for the second one, which is here. And let me see if this would work. I think this should be okay for now. So let's see if this works. We should have converted in the vertical direction. So I'll just do a test. Let's see. It just has one because we are not calling grow. Let's enable this grow, do a test, and voila. So now we have a three-dimensional tree structure growing in the random direction. So you can actually see how this is procedurally generated by moving the slider. So you can see it's actually changing its shape because every time I'm calling this function, the random is changing. So we can fix it by doing random.seed and define some variable here. That's all it takes actually. So if that constant is simple or fixed, then you can see that my growth is actually working like so, right? So this is a structure growing in 3D. Now there are a few things we would like to add to this, of course, which is basically we want to control the random angles. So this is always bifurcating at the same angle, which is -15 to 15. So that's why it's kind of deterministic. Only the random angles are different. So we can also do it like this. So rather than using maybe -15, we can define or customize the interval, right? So we can do random.uniform, and we can do minus angle minimum, and so we can do a min and a max. So that will give it actually we need to a min 0. Actually we can do a angle. Let's do it single angle. Yeah, that will be the that's actually all we need. And for the second one we can do 0 to angle, right? So that's it, and that will do it. So we need to define a new variable here and call it angle, and for that one I can define it to be 30, and this controls how much we want it to bifurcate, right? So we can control the angle using this variable now. So that is working. This is working as well. So let's see what we can add. We actually want to also do maybe we can also input some distance threshold. So that distance could be maybe we can add it here. So we can add a length, and we can pass in 5 as the initial length. We can also use it as a variable, and that length we want to diminish it at the end. So we can take this parameter and we can do length times random dot uniform, and we could do 0.75 to 0.95. So there will be some we can decrease the length a little bit and do it for both of them. And then we want to use the length to scale up the vector, right? So here we're creating the vector v1, and we can here scale it up. So v1 equals rs dot vector scale, and we can do v1 and length. We can do the same thing here, v2 dot length. I could have also done it to v, but maybe this is better because actually we might have to do it uniform at the end. Let's see. We can actually do it inside the point add. So rather than putting it here, we can do it here. So that actually doesn't override v1. That's actually a bit better because if we take these lines out, we are scaling it up to move the point, and we are not overriding v2, so v2 will stay normalized. And that's actually how it looks like now. So we can define a length here. Let's say the length is 5 as well. So I can have an input here, call it length, and pass it here. And that length, we can actually, let's make it just simply capital L, and we pass in that capital L here. And I also want to customize it here. So we were adding the first branch to find B. So we can do rs.vector scale. We want to scale V with L, right? So that will also define the first trunk. Rs.vector scale. There it is, test, okay. So this will control the total height of the tree, and this will control the angle, and this will control the number of generations. We can also add another variable for the seed, but I think this is kind of okay, what we have at the moment. Now the final step is about turning these to curves. So I'm actually going to draw what I want to do, so you can here see if I bake these curves. Let's enable them. So if I bake these, you can see that there's a line here, but what I want to do is rebuild this line. I want this point to be on top of the first point, and I want this point to be underneath this point, so that we have these sorts of curves instead of straight branches. And to do that, we need to find these two new points. So this point is kind of upwards to this point, and the third point is below the fourth point, right? So we need to define or find the locations of those. So we can do that inside the code. So here I was finding point 1, and afterwards we can also find the two new points. So we could do, let's say m1 equals, we can straight up copy point's x coordinate because it's above the first point, and we can copy its y coordinate. But for z, we want to add to points z coordinate kind of the difference. We want to find the difference from point 1 z minus point z, and we want to multiply it by, let's say, 0.5, right? So that will define the point, the z location for the point. So we're going to find almost the mid height actually. So we're going to add it to point 2, and I think this should work because point 1 is above point. So that will be point m1, and for m2 we want almost the same thing for z, but we want point 1's x and y, right? So I just edited these parts, and we don't want to create a line anymore, so I want L1 to be a curve. So we could do L1 equals rs.addCurve, and we can define the points in the array. So we will start from point, go to m1, go to m2, and then go to point 1. So let's see if this works, and I'll do test. There you go. So these converted to Bezier curves now, and all I have to do is do the same to the second one. I can also use different variables for these because I'm using m1 and m2 there. So let's call these m3 and m4, and all I have to do is replace 0.1 with 0.2. So that's all it would take. And for L2, we will do, I'll just copy this line, make it L2, and this will be M3, M4, and this is 0.2. And do a test, and the other part is done as well. So that's basically how we converted the straight lines to curves so that we can actually do nice pipes around them to visualize the tree branches. So let's actually create a seed value variable as well. So I'm going to create an S variable here. So let's make it S. And I can define a new variable here. And so we can actually customize our tree. And this is the first part of the exercise, but basically what we want to do is now pipe these curves. You can simply do a pipe here, which will give you, I guess, nice geometries like this, but the thicknesses would be uniform. So what I want to do instead is make the trunk kind of taper towards the top. So in order to do that, we're going to write some simple code in Grasshopper. So we can output these curves now, and we can start with the endpoints of these curves, which are located here. And then what I want to do is calculate the boundary of the tree. So I want to find the interval for the maximum value. So we can do deconstruct the starting point and the endpoints. And then I can look for the bounds of the z values, right? So I can stream them into the same, and then we can find here that 8.35 is the total height. And then we can deconstruct that domain. And here we are going to normalize using this value. So this is the maximum value. And these are the corresponding z values. Notice that it starts from 0, right? So the value that we want to have the greatest radius is the smallest. So we need to basically reverse this type of mapping, and we can do that by first subtracting the maximum value from the z values. So like that, and I have to do it for the two ends of the curves. And then I can also divide to normalize them. So I can divide these values to the subtracted versions. And what this will do is we will have a normalized value here from 0 to 1. And when it's 1, it will have the maximum radius, right? So that's essentially, we converted them into kind of a percentage. And we can also now do a variable pipe. So I can do pipe variable. My curves are here, so I'm going to pass in the curves. And I have 31 curves. Here I have 31 values, and I need to actually put them in doubles. So I can do a weave with grafts here. So this value is for the base. So starting points are at the bottom. So this is the bottom value. This is the top value. And this will be a grafted line now. So because this is grafted, the circles, the curves have to be grafted too. So I have to graft here. And you can associate a panel here. For pipe variable to work, if we have a curve, basically you need to supply the parameters where those radii values will be. For our case, they'll be at the beginning and at the end. So I need two values that are 0 and 1 for the curve. For the curve to work, and I'm going to do 0 and 1, and we need two data here. These are the t values, these are the pipes. This one didn't necessarily work. I guess we need to, because the lengths are changing, if you right click here and do reparameterize, that will actually take care of it. So we can also multiply this with some coefficient, because we are outputting the radii. So here you can add a custom radius value and multiply it with that. So this is a bit thicker, but we can reduce it. You can see that it's always tapering. And you can also add an upper threshold. Notice that it's always going to 0 for this point, but you can do a maximum here. and filter out kind of the values that are below 0.2, right? So this will go here, and that will set the values to not be smaller than 0.2, so that could filter the data. And we can actually bake this now, so let's bake it, and that's our tree. So I'm going to delete these, and we can output some cool trees actually. Let's play around with this a bit. I'm going to move to shaded view. Actually, let's move to rendered view. That was the first one. We can actually increase the length. We can change the angle. We can control it any way we want. We can also change the amount of generation. That's a bit different. So let's reduce the angle so it goes up. This was the seed value, so we can output different generated trees as well. So this is, don't forget, this is L system, so it's a generative function that we have written, and it's always bifurcating lines. So right, so these are the different variations. So that's another one. Let's output a third one, so we could reduce the angles a bit. Generation, let's keep it at 6. We can reduce the length, increase it. We can also play around with the seed and see what we get. Okay, there it is. So that was basic branching using L system. So I tried to make it as interesting as possible. I hope you like this tutorial. You can also find other resources on this website, and if you would like to learn anything else, you can just leave a comment below, and I would also like if you subscribe to the channel, and thanks for watching.